Okay, so now that we understand how to find a derivative for f of x at a particular point, or any point p, through limits, then we can also be able to prove or understand more in detail where our derivatives might fail to exist and why. So there are actually 4 different instances where derivatives fail to exist. And the very first one that I'm describing is a corner. And this is the one that I've been referring to in previous lessons because it's the first one we saw when we were talking about that absolute value function and how at that bottom of the V or top, depending on the transformation, there are 2 different derivatives, and you can't have 2 different answers. There has to be one answer. So the derivative didn't exist here, but now we're going to prove it. Okay, so 1, a corner. So the one-sided derivatives differ. Okay, for example, for f of x equals the absolute value of the quantity x minus 2, there's a corner at x equals 2. So let's actually do a right-hand derivative and left-hand derivative. Actually, let's do the left one first. So if we take the limit of our fraction, h is going to approach 2 from the left. Okay, I'm sorry, 0. 0, 0. This is always 0. Typo. That's okay, because h is in our denominator, but we're looking at 2 from the left. So we have our function, and we're going to do 2 plus h minus f of 2. And so f of 2 is 0, so we'd be subtracting 0. And if we plug 2 plus h into our expression, or h plus 2, we just get that absolute value of h. Well, we have 2 scenarios, okay? So from the left side, that means that we have negative h over h, and that becomes negative 1. My limits writing is a little sloppy here. So we end up with this as our left-hand derivative. So let's look at our right-hand derivative. So the limit of f of 2 plus h minus f of 2, that was supposed to be a plus, over h. Now as h approaches 0 from the right, so the limit of this minus that over h. So it seems like it's the same thing, but remember we're going from the right-hand side, so that absolute value is the positive h over h. We finish writing the limit. And so the limit of this, as h approaches 0 from the right, is really just the limit of 1 as h approaches 0 from the right. And that answer is 1. Completely different answers here. Okay, so when your one-sided derivatives differ, okay, they exist, but they're different, you have a corner. Okay, if you didn't get the last slide or any of the notes, please make sure that you stop, pause it, write it down. These are your notes. You need to know these. The more you practice them, the better you're going to get at doing them. So the second instance in which a derivative fails to exist is because it results where there seems to be a cusp. A lot of students look at them and try to say if it's really sharp, it looks like a corner, it's not a cusp, or vice versa. It's a cusp, it's not a corner. These two tend to be kind of looked at as the same thing, and they are very different, and that has to do with your derivatives. Okay, so be very careful. So here the slopes of your secant lines approach positive infinity from one side and negative infinity from another side. And so we're looking at our common function f of x equals x to 2/3 power, saying that there is a cusp at x equals 0. So let's take a look at our function here. So 0 plus h minus 0. Typo. Okay, so our slope of our secant line turns out to end up being h to 2/3 over h, okay, and this becomes h to the negative 1/3, okay. So if you were to look at the graph of this is 1 over the cubic root of h. This is what they're describing in the definition, but let's continue to look at our derivative here. Okay, so it's true that h to the negative 1/3 power as x approaches 0 from the left is negative infinity, as x approaches 0 from the right is positive infinity. So let's actually kind of simplify our derivative here. Okay. Okay, so if we do the direct substitution, okay, we're getting 0 to the negative 1/3 power, which again, this is something we cannot actually calculate. So this is where our graph would come into play to tell us that we don't have an answer, but that we have negative infinity here. Okay. And that's why I mentioned about the slope of the secant line, because we can't finish the limit without actually taking the look at what our graph is for the slope of the secant line. Okay, so this is our left-hand derivative. And our right-hand derivative is the positive infinity. So it turns out that this is what we get for when we look at as h approaches 0 from the right. We get positive infinity. Let me take a quick picture of my calculator so that you can see it and understand that you get different answers, and our answers have to do with infinity and negative infinity. Okay, 2 different infinity answers. Okay, so there you have it. We're up to number 3. Okay, so the third instance where a derivative may not exist is because there's a vertical tangent. Okay, and that's because when you're dealing with a slope that is 0, it's a horizontal line segment. But if you're looking at something that is a vertical line segment or a vertical tangent, as we're saying here, your slope is undefined. You're dividing by 0. So that's why your derivative fails to exist, because it's, dividing by 0. And we can't say that that's a value at all. So here we go, number 3. So it's saying the slopes of the secant lines approach positive infinity or negative infinity from both sides. So this is different from number 2. When I ended number 2, I said you have both positive infinity and negative infinity. So 3, for vertical tangent, one answer is going to be positive infinity, and so is the other. Or one answer is negative infinity, and so is the other. So let's take a look at this function here where there's a vertical tangent at x equals 0. Okay, so left-hand derivative. We take the limit as h approaches 0 from the left, and again our vertical tangent's at 0. So if we plug this in, when we simplify, we end up getting h to the 1/3 power over h. And, we have to keep simplifying. So that's the limit of h to the negative 2/3 power. And again, we need to kind of look at the graph of this to determine its value. So I'm going to pull that up in a minute while I write out your right-hand derivative. And it looks the same thing, but it becomes a different answer because now we're looking at as h approaches 0 from the right of this expression. If you're wondering how I'm getting the exponents, remember 1/3 has to be subtracted from 1. So it's 1/3 minus 3/3, and that's a negative 2/3. Okay, so we're going to look at these on its graph. Okay, and as you can see, as h approaches 0 from the left-hand side, it's positive infinity. And as h approaches 0 from the left-hand side, it's positive infinity. They're both the same. We have a vertical tangent, okay, for your graph. And that is your vertical tangent. All right, one more. If I go too fast at some spots, you can pause or stop it. Make sure you get this into your notes, especially even the sketches, so that you can see, like how I pointed out, there was a vertical tangent, or I'm circling, there's a discontinuity. These graphs are also important, okay, as opposed to the ones that we're using to evaluate the limits. You should know how to evaluate limits graphically by now. Okay, so fourth one in which a derivative does not exist is, well, a discontinuity, as I just said. Okay, so one or both sides of the one-sided derivatives will be non-existent, and let's take a look at this example here. So we have here f of x, and it's saying there's a discontinuity at 2. So this is your right-hand derivative. I kind of went around about. I always started the previous slides with a left-hand derivative. So let me do that. I want to stay with some consistency here. Okay. So in this particular problem, f of 2 is not actually something we can evaluate. Okay. Well, let's see. So we can plug in the 2 plus h, or h plus 2, into the absolute value here. But the problem exists is evaluating when x is 2, because you're going to end up plugging it into this function, and you're going to end up getting... Actually, let me erase that. The absolute value of 0 is fine, but the division of 0 is not fine. We can't actually finish this, okay? So even though we end up with this part being okay, we don't actually have an answer here. So it's non-existent, okay? This is undefined. It's not defined when x is 2. So this limit is non-existent. Okay? So we don't have a left-hand derivative, and when we try to do the right-hand derivative, same thing's going to happen. So it says one or both. In this case, it happened to be both are non-existent, so we have a discontinuity. Okay? So be careful, because maybe you'll find one from doing either your left-hand derivative or right-hand derivative, whatever you want to start with first, but then the next one may not be, or it could be this case where it's both. In any case, we're done with our 4 instances, and keep practicing. Good luck.